A, Z, and N are the symbols used for mass number, atomic number, and number of neutrons respectively. Here's a graph of N against Z. As you can see, isotopes generally sit above the N equals Z line, which means they have more neutrons than protons. The further they are from this curve, the more unstable they are, and the more likely they are to decay to get closer to the curve. Lighter isotopes are generally beta minus emitters, heavier isotopes are alpha emitters. Beta plus emitters don't exist naturally as they require proton doping to produce the right isotopes, which puts them under the curve. We can zoom in on this graph to show the decay chain an unstable isotope will move through. They can also take different routes to end up at the same stable isotope. They're always diagonal lines in this case, but just be aware that you could also get a graph of A against Z instead. In this case, you get a horizontal line for beta decay, as the mass doesn't change. Briefly, metastable states. Gamma emitters aren't drawn on these graphs because, of course, the nucleus doesn't change. What usually happens is that an alpha or beta decay occurs, leaving the nucleus at an excited energy state, much like an electron. It will usually de-excite instantly, emitting a gamma photon as well. This means it's hard to get a purely gamma-emitting source. However, some isotopes can decay and then remain at the excited state for a long time after that before releasing that photon. This is called a metastable state. The example we usually use is molybdenum-99. This decays via beta minus, leaving technetium-99 in a metastable state. This is then filtered from the undecayed molybdenum to then be used as a pure gamma emitter for uses such as medical traces or radiotherapy. In reality, the relative mass of nuclei is based on the relative atomic mass unit U. This is defined as 1/12 the mass of a carbon-12 atom. And we find that neither a proton nor a neutron have a mass of exactly 1 U. Even if a helium nucleus had a mass of exactly 4 U, if you manage to split it up into its constituent nucleons, 2 protons, 2 neutrons, it will end up having a mass of more than 4 U. How's that? It's because it requires work to do that, to separate them out, to overcome the strong nuclear force. This work is turned into mass, and we use E equals delta mc squared for that, delta m being what we call the mass defect. What's the difference in mass between before and after? Of course, E equals mc squared involves joules and kilograms, which means you'd have to convert the mass from U first. But here's the shortcut. 1 U of mass converted into energy gives you 931.5 mega electron volts. This will be in your formula sheet. It's a much nicer conversion factor to work with. If we draw a graph of average binding energy per nucleon against mass number, we end up with this shaped graph. Now, to all intents and purposes, average binding energy and total binding energy of all particles involved follow basically the same patterns, so they're essentially the same thing. So maybe that will help you understand what's going on here. Remember that binding energy is the energy needed to separate a nucleus, which means that the one at the top requires the most energy to separate out the nucleus. This is the most stable isotope, therefore, and it happens to be iron 56. That's why an iron core can be left at the center of a star that's used up all of its fuel. The little spike on the left is helium-4, by the way. It's an uncharacteristically stable isotope compared to its immediate neighbours. That's why it's emitted during alpha decay. However, when nuclear events occur, such as fission, fusion, or decay, they don't involve nuclei being completely split into their constituents or vice versa, but rather just turning into other nuclei which are more stable, meaning they always move up the curve, as their total binding energy, and therefore their average binding energy per nucleon too, has increased. We can think of them as falling down a potential well, meaning they would need more energy to get out. Fission is the splitting of a nucleus, whereas fusion is the joining together of them. In both cases, energy can be released so long as the binding energy has increased. They fall down this imaginary potential well, and therefore climb this curve. That means that isotopes to the left of iron 56 release energy if they undergo fusion. To the right of it, the same is true if they undergo fission instead. If you're asked to calculate the binding energy in an interaction, all you have to do is find out the mass defect in U's and then times by 931.5 to give you the binding energy in mega electron volts. Fission usually needs to be induced. For example, a uranium-235 nucleus in a nuclear reactor's fuel rod will absorb a neutron, turning it into uranium-236, which is more unstable, and it splits roughly in half, producing 2 or 3 more neutrons that go off and do the same. In the process, energy is released, most importantly as kinetic energy, which heats up the coolant, often CO2, which then supplies heat to turn water into steam to turn a turbine, etc. Hence why such a reactor is often called a thermonuclear reactor. The neutrons released from fission are actually travelling too fast to be absorbed by the uranium nuclei, so they must first be slowed down by a moderator, usually water or graphite, to what we say thermal speeds. A reactor doesn't have an off switch though, so control rods are used to increase or decrease the rate of fission. Often made from boron, neutrons will be absorbed by them without causing further fission. They're lowered or raised between the fuel rods depending on the output needed. Don't get confused with the moderator. It's not there to slow down the reaction. In fact, it's the opposite. It speeds up the rate of fission by slowing down the neutrons so they can be absorbed and cause fission. Nuclear waste is awful stuff. It's hot and very radioactive, so it must be disposed of safely. It's left to cool in ponds first, and then it's vitrified in glass, which is non-porous, and stored deep underground away from water sources or fault lines, so there's a near zero chance that it can affect living things. Activity is given by the simple equation A equals lambda n, where n is the number of undecayed nuclei, not neutrons in this context, and lambda is the decay constant in seconds to the -1, but it could also be another unit for time to the -1 instead. The decay constant is the probability that a single nucleus will decay in that amount of time. I've dropped the minus that's sometimes in the equation, as that's only important when deriving the exponential decay equation, which you don't need to do for your exam, so we're not doing it now. But the equation is this: A over A0, that's just activity at time t compared to initial activity, is equal to e to the power of minus lambda t, where t is the time and the unit of that must be the equivalent of the decay constant in order to work. You might see the equations written differently in your formula sheet, but I think it's useful this way for us to see that it's merely a ratio of activity now to initial activity. So it's just a number between 0 and 1. It also works for n over n0, that's the number of nuclei left, and mass 2. If we need to rearrange for lambda or t, we do the natural log on the other side. You might say ln if you're weird. So natural log of A over A0 equals minus lambda t. The minus is important here. If activity is halved, the time t is the half-life by definition. So that's where t half equals natural log 2 over lambda comes from. If you're given a graph of activity, you'll invariably have to find the half-life from it and then calculate lambda as natural log 2 over this half-life. Then reuse lambda in the full equation. As gamma radiation is emitted in all directions, it falls away inverse squarely with distance, so intensity is inversely proportional to distance squared, so we can say that I1d1 squared equals I2d2 squared. Intensity can also be replaced with count or count rate, the amount of radiation detected over a certain time, say a minute. Don't forget your background count, of course. If you draw a graph of count against 1 over d squared, you'll likely get a straight line that doesn't go through the origin. This is because the distance measured won't usually take into account that the radiation isn't being absorbed right at the end of the tube, so there might be a systematic error of a couple of centimeters or so. If the graph curves when you get close to the source, then that implies that there's probably some alpha or beta being emitted as well. You should remember from GCSE that it was Ernest Rutherford who discovered that the nucleus was positive and small relative to the size of an atom. But he also estimated how much smaller it was too, by comparing the number of alpha particles deflected back through an angle greater than 90 degrees to those that went through. This proportion gives you the ratio of the area of the target circle of the nucleus compared to the atoms. The root of this gives you the ratio of the diameters. However, a more accurate way of measuring the diameter of a nucleus is with electron diffraction. As you know from quantum, electrons will create a diffraction pattern when incident on atoms or nuclei. The angle between the central max and the first order can be used in our diffraction equation d sine theta equals n lambda to find the diameter, lambda being the de Broglie wavelength. If you plot a graph of any log of the radius against the log of mass number a, also the number of nucleons in the nucleus, we get a straight line with the gradient of a third, and a y-intercept we can say is equal to log r0. Combining the right side and delogging, we end up with r equals r0 times a to the power of a third. Often you'll be asked to compare two nuclei to find an unknown radius or nucleon number. So as r is proportional to a to the third, we can say that r1 over a1 to the third is equal to r2 over a2 to the third. Leave a like if you found this helpful. I've also put these into videos that cover whole papers. Click on the card for your board if it's there, or go to my channel for more, including international boards.